So this is the PDF of the alternative current lesson. Alternating current is a current which keeps alternating with time. Can you say that that's positive and it's a positive current and the negative current, and so it keeps alternating with time. It's called alternating current, and this is what is called I0, which is the maximum current, and this EMF graph is like this. And again, I've drawn a sine graph. As you can see, sine 0 is 0, sine 90 is 1, sine 180 is 0, sine 270 is minus 1. So obviously I've drawn a sine graph, and this E0 is the maximum EMF. The amplitude of the EMF is always greater than the amplitude of the current, and you should know the basic relation, such as I've taught you I is equal to I0 by root 2, where this I is called IRMS value, or a root mean square value, which is I0 by root 2. And there's something called I average, okay, an I average value, which is 2 by pi of I0. Basically, because the current is continuously varying, we should be able to speak about the current in terms of either peak value of current I0 or RMS value of current, which is root mean square value of current, and I average value of current. And if you see, this is 0.7 times I0 by root 2, which is 0.7 times I0, and the 2 by pi, which is approximately 0.6 times I0. So which is closer to the peak value? I0 is 0.7. IRMS is greater. We take IRMS values everywhere when calculating in this whole exercise. We don't take I0, not much with I average too. So we stick to IRMS. What is IRMS? The word suggests, as the word suggests, is root mean square value. So you have currents such as I1, I2, I3, positive side and negative side, you know. So it's I1 square, root of I1 square plus I2 square, say 3 currents, I3 square by 3 will give you IRMS, a root, mean and a square. That's what's called as RMS value. So that's how we calculate the RMS voltage too, and the relationship between IRMS and I0, which is the peak value of current. I0 is the peak value of current, as IRMS equal to I0 by root 2, ERMS equal to E0 by root 2. And I average is 2 by pi I0, which is 0.6 I0. We don't use much of an average value here. And basically, you should know that the RMS value, they have got the RMS value by the amount of heat produced. They pass DC current. You know, the DC current and the AC current is similar for the first T by 2 time period. For half the time period, they are just the same. It's during the second half the AC gets negative, whereas the DC proceeds like that. So that's a basic difference between a DC and an AC. And so for half the time period, we can say that both of them behaves the same way. Or in other words, you know, they are passing a DC current through a circuit. They are looking at how much heat is developed across a resistor. Across the resistor, how much heat is developed. The same heat must be developed when they are passing the AC current. That amount of AC current they will pass so that the heat remains the same. And based on the heat remaining the same, the value of the current is what is called RMS value. That's what is IRMS. So then, can you see the definition here? The value of the DC, the value of the DC current, which produces the same amount of heat in a given resistor as is produced when AC is passed through for the same amount of time. That is called IRMS, which is I0 by root 2, and I average will be based on the charge flowing through. For they will pass a DC through a circuit. They will find out how much is the charge that is flowing through the circuit. The same amount of charge must flow through when AC also is passed through, and that's how they compare and arrive at an average value. So the value of DC, which sends out the same amount of charge in a given circuit as is sent through a AC, as is sent through by an AC when it's passed through the same circuit for the same amount of time. So that is what is the definition. You understand what is the RMS value is arrived at because the heat produced in a resistor. An average value is about the same amount of charge that is flowing through the circuit. So that is how they arrive at some value which is relatable to all of us. You know, if I'm talking about IRMS, you will also be talking about IRMS value. If I'm talking about I average, you know what is I average, and you'll also talk about I average. It's like if I talk in terms of centimeter, you'll talk in terms of centimeter. If I talk in terms of meter, you'll talk in terms of meter. So as simple as that, you know. So we'll have to have some understanding between us. When I deal with RMS, we deal with RMS. When I deal with peak value, which is I0, I deal with peak value. And the relationship between IRMS and I average with I0 is already known. Okay. So let's look at this sum where you have calculated RMS value. It is like a digital signals. Can you see it's either 2 amps or minus 2 amps or 2 amps and goes on the circuit. This is first second, it's plus 2. During the second it's minus 2. So I RMS value is root of I1 square plus I2 square plus I3 square by 3, which is 2 the whole square. The negative side is minus 2 the whole square, but doesn't matter, it becomes positive. Plus 2 the whole square by 3, thus you get 2 amps to be the IRMS value of the current. Incidentally, which is the same as the current that is specified in the graph too, but RMS value is 2 amps. So next is what is the phasor diagram? And let's take a graph. I told you we can represent the EMF for the current as a sinusoidal function. Sinusoidal function is sin 0, 0, sin 90 is 1, sin 180 is 0, and the graph goes on like this. This is a current, and I'll in fact indicate it in purple color, and this represents the current, and the EMF, let me do it in green color. This represents the EMF, just to show that the EMF's amplitude is greater than the current's amplitude, and this is E0, and this value here is I0, the peak value. And since they both are the same phase means starting at the same point. So then how do we do a phasor diagram? Any sinusoidal motion can be represented in the form of a rotational motion, as 0, pi by 2, pi, 3, pi by 2, 2 pi. So it can be represented, the waveform can be represented as rotational motion too. The first thing that I'll do here in a phasor diagram is to draw E0 and mention that this E0 is making an angle omega t with x-axis. Since the current is in phase with E0, the EMF, so I can do this as I0, which is a much smaller amplitude, and complete a circle. This shows the current and EMF are in the same phase. And so if I write E as E0 sin omega t, current will also be I0 sin omega t. Okay, so when there is a phase difference is there, supposing, look at this, can you see that EMF started at origin, EMF is here, which is E0, whereas I0 is slightly ahead, current is ahead. The fact that the current is already here shows that it's ahead of the EMF. And this is my, this is my I0. Yeah, and so the phasor representation, first I'll draw E0 to show that it's making an angle omega t with x-axis. And this I know that I0 is ahead. So I'll draw an I0 which is ahead by phi. Can you see? Ahead by phi, and I0 is ahead by the EMF by phi. And this phi is known as the phase difference. And so you start with E is equal to E0 sin omega t, and you end up writing I is equal to I0 sin omega t plus phi, where phi is the phase difference. So you understand how we represent the EMF I current can be ahead of EMF, or even lagging behind EMF, or the same phase, and how the phasor diagram is drawn. Okay, rotational motion representation. So what happens when the circuit has got a pure AC circuit has got a pure resistor, just a resistor and an AC source. So you draw a resistor here, and an AC source is connected to an AC source. An AC source EMF is equal to E0 sin omega t, we all know that. And what do you know about the resistor? P is equal to IR, but you say E is equal to IR instead. Yeah. So because E is equal to E0 sin omega t, you take this expression E is equal to E0 sin omega t, divide both sides by R. So you get E by R is equal to E0 by R into sin omega t, where this is of the form, this itself is I and this itself is I0. So I is equal to I0 sin omega t. So started with E is equal to E0 sin omega t, ended up with I is equal to I0 sin omega t, where I0 itself is E0 by R. Just equating this. Therefore, you know that the current and the EMF are the same phase in the resistor. Nothing is ahead. They both are the same phase, and you know how to draw same phase for a graph as well as for a phasor diagram. So next is current which has got with AC circuit which has got an inductor. So AC circuit which has got an inductor and this is an AC source, and E is equal to E0 sin omega t, as you know. And what do you know about the inductor? You know the inductor's EMF is minus L into di by dt, and applying a closed loop to this circuit, in a Kirchhoff's loop rule, in anti-clockwise direction, sum of all the potential is equal to 0. So E minus dl by dt is equal to 0. So E is equal to L into di by dt. First is this. If you forget this, you won't know how to do it. So E is to be written as E0 sin omega t. Take the dt to the other side, and you can integrate both sides. And L can be taken out, and integration of di is 1 di, which is I. So you get an I here. E0 can be taken out, and integration of sin omega t is minus cos omega t by omega. Minus cos omega t by omega. is integration of sin omega t. You all know that the differentiation of cos x is minus sin x. So the integration of sin x will be minus cos x. So it's minus cos omega t, but chain rule you have to divide in integration. You can't write into omega, so by omega. Now bring the L also down. So it becomes L omega the denominator. And this is similar to, I can't get an answer in cos omega t. I have to get an answer in sin omega t because I started with the sine graph. I should end up with the sine graph. And so cos omega t can be written as sin 90 minus omega t using complementary angle. And bring the negative sign inside, becomes sin omega t minus pi by 2, where the phase difference is pi by 2. This itself is of the form I naught sin omega t minus pi by 2, where the phase difference is pi by 2, and I naught itself, is E naught by L omega. I naught itself is E naught by L omega. Yeah, can you see here? So write that separately, where this L omega can also be called as XL, which is known as inductive reactance. This XL is known as inductive reactance. It's like resistance offered. Can you see I is equal to E by R? Instead of R, you are having an XL. That shows that it's also kind of resistance, but it's offered by an inductor. Okay, and XL is equal to L omega. So then that completes this, and you know that the current is lagging behind. Can you see the current is lagging behind? EMF is E naught sin omega t, but current I is equal to I naught sin omega t minus pi by 2. So how do I do the phase diagram? First thing, first is doing the graph. You can start the EMF from 0, and you can do bigger amplitude of EMF, and current is in an inductor. It starts with the letter I, but current I is lagging behind. So then, therefore, lagging behind, I start here. And when at peak value, EMF is at peak value, the current is at 0, because it's lagging behind by 90 degrees. When EMF is 0, the current is maximum. And you can do the graph like that. And phasor diagram, after doing by x-axis and y-axis, first thing that you do is E naught, which is making an angle omega t with the x-axis. And the current is lagging behind by 90 degrees. So you do a current here, which is I naught, which is lagging behind by a 90 degree, and this is I naught. And you can complete the circle to represent the phasor diagram so that it looks more beautiful. So let's go to an AC circuit containing the capacitor. What do you know about the capacitor? V is equal to Q by C. That's the fact you know about capacitor. So write that, and if you forget that, you can continue with the derivation, where V is nothing but E, which is E naught sin omega t, is equal to Q by C. Take the C to the other side, and you differentiate. You'll differentiate Q. I'll get current. So I understand that I've got to differentiate in order to get I. So differentiate that. That's quite simple. Sin omega t differentiation is cos omega t into omega. E naught and C are constants, so you get this. And you can't get an answer in terms of cos, you have to get the answer in terms of sin. And the C omega can be written as 1 by C omega, because you need E naught by resistance, or an XC. As an XC is equal to 1 by C omega, which is a capacitive reactance. It's a resistance offered by the capacitor. In other words, it's 1 by C omega XC, capacitive reactance. We don't call it as resistance. And you have to convert this cos omega t into sine. And how do you do that? You write it as sin 90 plus omega t in the second quadrant, so that sine is positive in the second quadrant, and you know that current is ahead of the EMF. So when you draw a phasor diagram, you do an E naught, which is making an angle omega t with x-axis, and your current is ahead. Can you see the current? I naught is ahead by 90 degrees with the EMF. So you can complete the phasor diagram, and you graph. You always draw an E naught starting from the origin, and current is ahead. So current is above the, somewhere here, and it's ahead by 90 degrees. So when this is maximum, E naught is maximum, current will be 0, and so on. So that completes it. Shows that in a capacitor, current is ahead, EMF is lagging. In an inductor, current is lagging, EMF is ahead. Okay. So now comes an LR circuit, where you have a resistor and an inductor. LR circuit and AC circuit. You know that this E naught sin omega t, which is the EMF here, is going to split among the resistor as a voltage IR, and across the inductor as IXL. And the component of EMF gets broken down for partly for resistor and partly for an inductor. You know that? Yeah. So then let's write individually what happens in a resistor. On the left side I've written what happens in a resistor individually is E is equal to E naught sin omega t. Current will also be I naught sin omega t, because with a resistor it's all in phase. With an inductor, current is lagging, so you write E is equal to E naught sin omega t, I is equal to I naught sin omega t minus pi by 2, just showing that's lagging behind. So now a combined diagram, a phase diagram is what is important. You draw an E naught here, which is making an angle omega t with the x-axis. First step. Break the T naught into two components. Blue color, can you see that I've broken it out into VR, which is the voltage across the resistor, and a VL, which is the voltage across the inductor. And you know that the current will be in phase with the resistor, so I can mark the purple color current along with VR, because there is no time phase lag between in the resistor between the current and the voltage. There is no phase lag. So then you observe that when you compare to the voltage across the inductor VL, the current is lagging behind. When compared to with the resistor, voltage across the resistor, the current is in phase. You get such a beautiful diagram, and the angle between I and E naught is what is phi, a phase difference always. Okay, so you know that it's no more 90 degree, because one is pulling it at 90 degree, another is not pulling it at all, the current, and therefore there is only a phase difference of phi which is less than 90. Yeah. So this is a vector explanation which you don't have to necessarily learn. You don't have to necessarily learn this. Just if you can understand, you can understand. Else forget it. I'm going to translate this into a diagram. According to your school, the horizontal is VR and a vertical is VL. That's been translated. And the E naught is the resultant, and E naught itself is Pythagoras theorem, root of VL square plus VR square, and it's E naught. So VL is inductance voltage, which is I naught into XL the whole square, and VR is I naught into R the whole square. So I naught can be taken out common, you get XL square plus R square. So I naught itself is E naught by XL square plus R square, where the denominator is mentioned as Z, which is called impedance. It is not called inductive reactance anymore because resistance is added, so we call it as impedance. And you can even do a tan phi from the diagram. Tan phi is opposite by adjacent, which is VL by R. So it's VL by R, which is I into XL by I into R, IA gets cancelled. So phi is tan inverse of XL by R. What happens when you have an AC circuit with a capacitor and a resistor? And the voltage gets split between a capacitor and a resistor. And you write what is happening when a purely capacitive circuit. What is happening? You see an arrow here. Purely capacitive, current is ahead. So you start with E is equal to E naught sin omega t, and write I is equal to I naught sin omega t plus pi by 2, and purely resistive, both of them are in phase. That's what I've written on the right side. I'm trying to do a phasor diagram where I'll always mark E naught making an angle with omega t with x-axis. The first thing that I'll do is that. And break the E naught into two components, but I have to do it carefully here. I should understand that the voltage in the capacitor, the current is ahead, the voltage will be lagging. So between the resistor and the voltage of the capacitor, the voltage of the capacitor has to be lagging. So I have to break down the E naught into two components, such as VR here, and and a VC which is lagging. And you know that the current will be in the same phase as VR in the resistor. So angle between I and E naught is phi, and phase difference is phi. And you can translate this into this diagram where the blue color is VR and VL, VR and VC, capacitance, and E naught is the resultant. And you can directly write what is E naught is root of VC square plus VR square. That's easy, no need of the vector form it. VC is I naught into XC the whole square plus VR is I naught into R the whole square. I naught can be taken out common, it's XC square plus R square. So thus I naught is equal to E naught by root of XC square plus R square, where the denominator is impedance. And we can also write what is tan phi, which is opposite by adjacent, which is VC by VR, IXC by IR. I and I get cancelled, tan inverse of XC by R. So let's go to next. There is an LCR circuit, inductor, a capacitor and a resistor. The voltage gets broken down into also three. Yeah. So I will have to break down into components like that. And the voltage in an inductor, current is lagging, so voltage is ahead. In a capacitor, the current is ahead, so voltage is lagging. And whereas in a resistor, it's going to be in phase. So write all those explanations. Those considering is equal to E naught sin omega t, I becomes I naught sin omega t minus pi by 2, I naught sin omega t plus pi by 2, and I naught sin omega t. And how do you do the phasor diagram? You always do an E naught, which is making an angle omega t with x-axis. That's your first step. And you have to break it down into components. You have to be very careful in doing this. you know that you have to draw a VR, which is horizontal component, and a VL, which is the vertical component, because you know inductor, the voltage is ahead. For an inductor, current is lagging, but the voltage is ahead. And whereas in a VC will be when compared to the resistor, it will be lagging behind by 90 degree. So therefore, the VL and VC must be at an angle 180, because this is lagging by 90. This, in other words, EMF is ahead by 90. EMF is ahead. The EMF is lagging 90, 90, 180. Therefore, can you see a VL and VC are right opposite each other? So now translate it into a school diagram where the blue color components are drawn like this, so that your E0 is the resultant. Yeah. So then it becomes easier, no need to calculate as vectors, you know, E is equal to, okay, considering this, you see that VL and VC can get cancelled because equal and opposite vectors may get cancelled. So in order to avoid that, you can consider that VL is larger than VC or XL strength is greater than XC, so that you get a vector which is VL minus VC here, and resultant E will be root of VL minus VC the whole square plus VR square. I can substitute I0 into XL minus I0 into XC the whole square plus I0 into R the whole square, where I0 can be taken out common, XL minus XC the whole square plus R square. You can write the expression for I0 is E0 by root of XL minus XC the whole square plus R square, where this whole thing is, denominator is called Z, which is the impedance again. Okay, impedance again. Here comes a case study. What happens if XL becomes equal to XC? I told you in the graph they will get cancelled out and there will be only resistor. So then I0 itself will be just E0 by, all this goes away and it will just be an R square here, yeah, and becomes R, E0 by R. The circuit behaves like a purely resistor circuit in that case when XL becomes equal to SC. Let's see what happens. When XL becomes equal to XC, you can see that this I0 is going to be even more maximum because the denominator is going to be lesser. So then the current is I0 is reaching a maximum value when XL becomes equal to XC, and XL itself is L omega and XC is 1 by C omega. So omega square is 1 by LC, omega is equal to 1 by root of LC. Omega can be written as 2 pi mu, so mu is equal to 1 by 2 pi into root of LC. So this is the current versus a frequency graph, omega graph. Okay, where you see that the current keeps oscillating between two frequencies, omega naught minus delta omega and omega naught plus delta omega, where this is delta omega naught is here, the gap is delta omega and the delta omega here, and the width becomes 2 delta omega. That's called a bandwidth. The circuit at some resonance frequency, omega naught is the resonance frequency, they call it as omega R also. It keeps oscillating to and fro between two frequencies, which is omega, considering it's omega naught minus delta omega and omega naught plus delta omega. It keeps oscillating between these two frequencies. And such a condition in circuit is what is called resonance of a circuit. The current keeps oscillating between two. When the current I0 is really maximum value, it's peaking value, you know, it's becoming sharp. The graph is becoming sharp. The current keeps oscillating between two frequencies, omega naught minus delta omega, omega naught plus delta omega, for a particular value of resonance frequency, and where 2 delta omega becomes the bandwidth, and this condition of the circuit is what's called resonance, at which the current becomes maximum. You know why it becomes maximum? Because XL becomes equal to XC, and that's the case study that we are doing. Okay, that will occur only in an LCR circuit when XL becomes equal to XC. Resonance will occur. So then let's come to something called a qfactor. A qfactor, you know, the central value is omega naught or omega R, which is resonance frequency. Yeah, the central value omega naught by 2 delta omega, the width bandwidth, which is called a qfactor, which is nothing but the resonance frequency by bandwidth. That's the definition for qfactor. So can you see that as the bandwidth decreases, I've drawn a purple graph, you see the bandwidth is reducing and the sharpness of resonance is increasing. It's called sharpness of resonance. Can you see the sharpness of the graph? It's called sharpness of resonance. A qfactor, in other words, is also called the sharpness of resonance. And you know the sharpness is obviously increased because it's omega naught by 2 delta omega. As delta omega becomes lesser, the sharpness of resonance, the qfactor, becomes more. It makes sense, right? So that completes that. You understood what is the qfactor and what's the sharpness of resonance. It's all the same. And as the bandwidth becomes lesser, the sharpness becomes more, the qfactor becomes more. Now here comes the derivation which is not a very important derivation. They've never asked this question in the last 15 years time. But it's important, it is there in the portion. So a derivation for qfactor or a sharpness of resonance. You may ask me, what is there to derive? It's just omega naught by 2 delta omega. No, that I'm going to derive in terms of the inductor in the circuit. Okay, so let's look at this. You know that in an LCR circuit is when this resonance is going to occur, and that resonance XL is equal to XC, and you get current is equal to E naught by R. You know all this. You know the graph is like this, and you're going to study. This is I naught, and you're going to study for some RMS value, I naught by root 2's value, which can occur on either side, I naught by root 2. I'm going to study for this position. And you know, when I naught is equal to E naught by R, yeah, here, I can write I naught for a position of RMS value is I naught by root 2, and E naught will become E naught by root 2. And so can you see that this resistance is eventually become root 2 R. Yeah, root 2 R. So you know impedance is equal to root of R square plus XL minus XC the whole square, but instead of its impedance here, write it as root 2 R. Yeah, because that's this position you are analyzing for this position, it is the root 2 R. And you know how it became root 2 R, I have given an explanation here. Substitute on the left hand side and equate it to root of XL R square plus XL minus XC the whole square, where XL is equal to L omega and XC is equal to 1 by J omega the whole square. Push the R square to the other side, squaring both sides, push the R square to the other side, you get R square is equal to L omega minus 1 by J omega the whole square, therefore R is equal to L omega minus 1 by J omega. And for this point where omega becomes omega naught plus delta omega, for this I naught by root 2 point here, I'm going to do a case study there. Omega naught plus delta omega by 1 minus 1 by C into omega naught plus delta omega, where omega naught can be taken out common. This is what is my effective resistance R now. Omega naught taken out, I'll become 1 plus delta omega by omega naught minus 1 by, again omega naught taken out, 1 plus delta omega by omega naught in the denominator too. You can take this up as minus 1 using exponents and apply binomial theorem. It will become 1 minus delta omega by omega naught. From by this 1 by C omega naught, I am going to multiply and divide by LC. So it will become LC, and you know LC itself is omega naught itself is omega naught is 1 by root of LC, omega naught square is 1 by LC. So you know LC itself is 1 by omega naught square. So substitute that 1 of the omega naught will get cancelled, and that omega naught in the denominator will go to the numerator. So it will become L omega naught here. So L omega naught completely can be taken out common, and you can open the bracket. You see that 2 delta omega naught by 2 delta omega by omega naught, which is the reciprocal of qfactor. So shift it to the left side and shift the R to the right side. So this becomes a qfactor. You notice a sharpness of resonance, which is L omega naught by R, which is XL by R. So you got a new formula for qfactor, which is inductive reactance to the resistance, ratio of inductive reactance to resistance. You multiply both by I. So you will also notice the potential across the inductor to the potential across the resistor. So you get another formula for qfactor or sharpness of resonance. So you get another formula such as, you know, from here, you know that XL is L omega by R, and omega itself is 1 by root of LC. So root L and L get cancelled. You get another formula which is 1 by R into root of L by C. So supposing they give you some Henry and Farad, you know, induct L and capacitor, capacitance of a capacitor, inductance of an inductor have been given, readily substitute 1 by R, you get a qfactor. So there are various ways in which you can find a qfactor, and this is a derivation for qfactor, which is useful only for learning the concepts and doesn't come for exams, but become clear, okay? Because there's various formulas, you know. And so next let's come to power factor. I still have to do eddy current, AC generator and a transformer, which I will do next class, okay? And let's look at what is a power factor. Okay, a power factor is power P average. P average is the power, which is, the formula is ERMS into IRMS into cos phi, where the voltage is ERMS value, the current is IRMS value into cos phi. You know that the current and the EMF will have a phase difference because we are talking about an LCR circuit. So you can simply write this, or if you ask me how it came, I am going to do a derivation next here. Derivation for power in an AC circuit. P is equal to VI V itself is E naught sin omega t, I is equal to I naught sin omega t minus phi. Yeah, in an LCR circuit, considering that inductor is more powerful than the capacitor. Now E naught and I naught club together, you get sin omega t and sin omega t minus phi together. You can multiply and divide by 2. People who are learning in, mathematics from me, it will be self-explanatory, I have done all this. So multiply and divide by 2, you can't integrate sin omega t minus phi together. So this is nothing but 2 sin A cos B, which is cos A minus B minus cos A plus B, which is 2 sin A sin B, which is cos A minus B minus cos A plus B. So this is A and this is B, apply that in cos A minus B, will be left with a cos phi, and a cos A plus B will be left with cos 2 omega t minus phi into dt. So when you integrate this, cos t is a constant, when you integrate this it will turn out to be integration of cos t into dt minus integration of cos 2 omega t minus phi into dt. So then cos phi into dt. So cos phi into dt, where cos phi is a constant, you can take out an integration of dt is just t. Okay. So then this will become integration of cos is sin 2 omega t minus phi by the chain rule by 2 omega integrated from 0 to t. So you are going to substitute small t wherever it's coming as capital T, or you can write a t as even 2 pi because the time taken and the full rotation or a full wave to complete is one full wave is 2 pi. So then sin of 2 pi or 4 pi, anything is going to be 0, so the second term becomes 0, and here it will be cos pi into t, and if taken power as dh by dt, yeah, and dt goes to the other side, that's how you integrate dh, get h. You can bring the t down, so it becomes power back again, and this 2 can be segregated as E naught by root 2 and I naught by root 2, which is E RMS into I RMS into cos phi. If you don't follow this, you can ask me once again in the class, I can explain to you. So this is how we get the power, and again this derivation is not important, they've never asked this. So this is what I am putting in here, when power factor, when I am calculating, I am writing power as E RMS into I RMS into cos phi with this P average. P average is equal to a virtual EMF, E RMS is also called virtual EMF, I RMS is a virtual current into cos phi, where this cos phi is called the power factor. And when you multiply the ERMS and the IRMS, when you multiply the virtual EMF and the virtual current, you get a apparent power. That apparent power has to be multiplied by the cos phi. The cos phi may be a cos 45, which is 1 by root 2, a cos 60, which is 1 by 2. So can you see the average power is lesser than the apparent power? So then a cos phi, which is power factor, is the ratio of actual power by apparent power in AC circuit. So that's the power factor, which is P average by E RMS into I RMS. That's cos phi. So there are various case studies we'll be doing on power factor, which will continue next class. I hope it's all clear to you. Okay, so I'll see you in the next class.